Okay, I guess we're ready to get started. Welcome to the Control Meets Learning virtual seminar. Thank you all for joining us today. For those who are joining us for the first time, this is a weekly seminar on various topics, broadly at the intersection of control theory and dynamical systems and machine learning. The format of the seminar is a 50-minute talk, followed by a Q&A period. If you have any questions, please post them on the chat box. One of the co-organizers will be monitoring the chat for questions. Or you may raise your hand and we will unmute you so you can ask your questions for the speaker directly. The talk is being recorded and will be available on YouTube. Today, we're delighted to have Professor Babak Hassibi from Caltech. Babak, of course, needs no introduction, as he's very well known in both the control and learning communities for his seminal contributions, as well as in other neighboring fields, information theory, signal processing, and communications. He is the inaugural Mose and Lillian Bone Professor of Electrical Engineering and of Computing and Mathematical Sciences at Caltech, where he has been since 2001. For many years, he was also the executive officer or head of the electrical engineering department, as well as the associate director of information science and technology. Prior to Caltech, Babak was a member of the technical staff in the Mathematical Sciences Research Center at Bell Labs, which I'm sure a lot of you are familiar with. And he obtained his PhD from Stanford in 1996. He has been named an ISI highly cited author in computer science and has received numerous awards for his work, including the PCASE US Presidential Early Career Award for Scientists and Engineers and the Packard Fellowship in Science and Engineering. Today, we're very excited to have him, and he's going to tell us about regret optimal control. So without further ado, let's welcome Professor Babak Hassibi. Babak, the floor is yours.
Thank you, Navid, for that kind introduction. It's a pleasure to be here. I know this is remote, but we'll do it with the best that we can with what you have. So yeah, as Navid mentioned, today I want to talk about regret optimal control. This is something that I've recently started looking at. I've begun to look at a few problems at the intersection of control and learning, and this is one of them. Perhaps the other ones I'll talk about in other occasions once they're more developed. This is joint work with three members of my group, Oron Sabag, who's a postdoc, and Gautam Goel and Shahin Lale, who are graduate students. Okay, so this talk, I would say, has much more, I would say, of a control flavor. It's kind of inspired by ideas in learning. You can tell from the word regret, perhaps, in the title. But it is at the intersection of learning and control, but more, control theoretic and, an approach to control that's really inspired, as I said, by learning. So to start off, control is a bit like life. It's how you live your life almost, right? So in life, whenever you're taking an action, say you want to decide, should I take this job? Should I go to grad school? Should I drop this course? Should I buy a house? Should I go on a date with this person? Whatever. Whenever you take actions, you base them on your past experiences, your knowledge, observation, everything you've accumulated through the past. But when you make a decision, of course, and in all of the examples I gave, I think clearly show that, it influences what kind of rewards you get in the future, what happens in the future, right? So it's not just an instantaneous action you take. The effects of the action propagate into the future and affect, what might happen to you in the future. Do I take this job or do I not, and things of that sort. The problem, of course, is that the future is unknown and uncertain. We're all confronted with this when we make decisions. in terms of what to do. And so people in life, have various philosophies, I guess, either known or unknown to them in terms of how they make decisions. And so in control, it's kind of like that too. And so broadly, one can categorize, strategies for control as for life, perhaps in the following way, right? So the question is what to do when you need to make decisions and take actions. So one option is just to ignore the future, and just optimize the present, right? I mean, let's do what's best for now. I don't know what's going to happen in the future. So that is a strategy. I'm sure many people who live their life perhaps like that. And such strategies are called myopic because they don't pay attention to the future. They're called greedy, so there's a whole host of greedy algorithms. And often, people are myopic or greedy when predicting the future, analyzing the future, or somehow optimizing what happens in the future is just too complicated. And so people take greedy routes, and sometimes it's not a bad thing to do. A bit more sophisticated, or perhaps a lot more sophisticated, is to make probabilistic assumptions about future events. So maybe based on your past or side information or whatever, you might have some idea of what's going to happen in the future, at least statistically speaking. And so if you have that, and if you can kind of maybe compute the probabilities of different events that can happen, you might be able to optimize the expected reward, right? So I will take this job because I think, chances are that it'll be a high-paying job, and, the economy will be good and whatever, and I'll be able to progress in that profession. But this relies, of course, on having probabilistic assumptions. And so the whole premise in control of stochastic control really relies on this fact, right? That there's stochasticity in the system, but we kind of know the statistics, and so we try to do control. We try to take actions that minimize, say, the expected cost. And so things like LQG control, Kalman filters, things like this all occur when you look at stochastic control. And again, I'm sure many people, live their life like this. They try to predict the future and take actions according to that. Of course, these models really rely on the fact that you know something about the probabilities. If you don't know them, or you make erroneous assumptions about them, then of course the actions you take may not lead to the results that perhaps you're expecting. And so with that in mind, another approach is to kind of just assume the worst and take actions that optimize the worst case, right? And I'm sure people who live like this, people who go in the basement and store up food and await Armageddon maybe live like this. And usually I would say that's probably not a very good strategy, but then COVID happens and maybe it is, who knows. But anyway, in the context of decision making, this is sometimes called pessimism, conservatism, being risk averse, and I'll speak about this a little bit. In control theory, things like H-infinity control kind of fall under this rubric of safeguarding against the worst that can happen. So you're sitting at the present, you look at the future, and you plan for the worst that can happen. Okay. And so I say, by and large, these are quite general viewpoints. As I said, you can even think of them philosophically. And so the question is that all there is, right? I mean, so we have designed controllers based on these types of ideas. And so what I want to talk about is another approach that, as I said, is motivated or inspired rather by machine learning, and that's the concept of regret. Okay. And so what do you do if you wanted to, say, design control or take actions based on regret? So the idea here is that you will take actions such that, at the end of the day or at the end of infinity or whatever, at the end of time, whenever, at your deathbed, hopefully 1,000 years from now, that you can look back at your life, all the decisions you made, and with the hindsight of knowing what happened, to have the least regret. Right? So the philosophy would be to live your life so that on your deathbed you have the least regret. Okay? So that is markedly different from what I described earlier. It's not a greedy approach. It has nothing to do with, predicting the future. And it really isn't about worst case. It's just trying to say that, I want to have a strategy such that if I look at all the possibilities that can happen in the future, compared to all of them, at the end of the day, I'll have the least regret. I'll take an action for which I will have the least regret. And I'll formalize this a bit more. But it's a different philosophy. Let's see what happened here. Okay. Now, the idea of regret, at least to my knowledge, was first introduced in statistics in the context of the multi-arm bandit problem. I'm sure many of you are aware. So there's multiple arms. Each one gives you a reward with, say, some probability at random, and you don't know what these probabilities are. And so in this context, people try to come up with policies to kind of, pull the handle, see what rewards they get, and try to converge maybe on the arm that gives you the best chance of receiving an award. And one measures the success of policies in terms of how much regret you have compared to someone who knows the probabilities that these arms will give you rewards. And so you want to minimize the regret. You want a policy that you will regret the least once you learn that, this is the arm that I should have been pulling. And so that's the first, I would say, at least to my knowledge, place where this idea comes up. It's currently widely used and formalized in machine learning. And I think the talk last week by Elad Hazan was generally, I think, in the direction of looking at regret in the context, again, perhaps of control. This talk will be a little bit different, or quite a bit different, as you'll see. Okay. And as I said, until very recently, I would say maybe the past 2-3 years, people had not really looked at it as a way of designing controllers. And even now, I would like to argue, I think prior to the work that I'm going to describe right now, it wasn't really considered for control. It was used perhaps somewhat for things like system identification and maybe learning in the context of control, but not for control system design itself, which I will be explaining. Okay, so informally, what do we mean by regret? I kind of described at a high level, but informally, we'll define regret. So there's some cost associated with our actions. I use the word reward a lot, but I will switch to cost from now on. And so the regret is essentially the cost that is obtained by a causal controller, meaning a controller that knows the current and the past, doesn't know what's going to happen in the future, and the cost that is obtained by a clairvoyant controller. So a controller who can take actions now, but who knows what the future measurements of the system, the future disturbances are, and so basically can take actions now as if the controller had hindsight of what's going to happen, right? And so, of course, a causal controller does not have access to that, and so we'll have a cost that's larger, and so this difference is generally non-negative, and what we want to do is minimize it in a notion that will become clear as we proceed. Okay, so that's the notion of regret. We're really just comparing ourselves to this unattainable, unrealizable clairvoyant control. Okay, so let's kind of get to it a little bit. So I'll introduce some of the math so that we're more concrete about what it is that we want to do. Okay, so I'm going to consider a linear time invariant state space model. So X is the state, it's n-dimensional, U is the input, it's m-dimensional, it's the control input, and W is some exogenous input. It's out of our control, it's generally not known. And I'll speak to what we know about it in a moment. And depending on the context, people sometimes call it the process noise or the driving disturbance. That's what W is. So the state evolves. It has an internal dynamic through the state transition matrix A, but is driven by the control that we can apply to it, as well as by this exogenous input that we don't have direct control over. Okay, so that describes the behavior of the system. In this talk, I will make the standard assumption for those of you who know these things, and there's a typo here. The pair A, B sub U is the matrix that maps the control to the state, I'll assume is stabilizable. If you know what that means, wonderful. If you're not, it's not that important. All it means that this system can, in fact, be stable through control, through the control input U. Okay, so I need to define what I mean by a policy. Okay, so the controller has to have access to some knowledge in order to control the system. And so we will assume it has some access to W, and I'll clarify what access that is. And so, for example, for a causal controller, you will only have access to current and past values of the exogenous input. It will not know the future values. But generally speaking, a policy is some mapping from the exogenous inputs, maybe restricted due to causality or other things, to the control inputs, okay? So it's basic, it tells us, you know, the policy is, it tells us how we map W to U, okay? The cost that we'll consider is the standard LQR cost. For this talk, I will look at infinite horizon problems, in fact, doubly infinite horizon problems. So imagine we're controlling from the infinite past to the infinite future. These results can be extended to one-sided infinite and finite horizon as well, though I won't do it in this talk. And so this is what I've written. Again, for those of you who are control theorists, you might, you know, feel a little uncomfortable that I'm summing things from minus infinity to infinity. I'm not putting it like a horizon t, dividing by t, taking the limit and all of that. That can be done. But for simplicity, I will look at this. And the reason I will look at this is because I will assume my disturbances, say, have bounded energy so that these infinite sums, this cost doesn't blow up. Those are technical issues, but I just wanted to keep the talk simple. So the cost basically is quadratic in the state, and it's quadratic in the control input. Q and R are given positive semi-definite weight matrices. And so what this means is that when we take control actions, we want to take control actions that are small because we want U transpose RU to be small. And we also want the state of the system to not grow too large. So that's the interpretation of these two terms. And, you know, we're doing quadratic control, so both terms in the cost are quadratic. Okay, so let me now a bit more formally describe this concept of regret. So I'm first going to look at the set of offline or non-causal policies. So these are all policies that can map, you know, the past, current, and future of the W's to past, current, and futures of U, willy-nilly. There's no restriction. So the control input at time 0 can depend on all the W's potentially. So I'm going to look at all offline policies. I'll call that pi off for offline. And so then the regret for a particular policy pi that the controller takes, which I'm writing is the regret, it's a function of pi, it's a function of the disturbance vector or disturbance sequence W. It's the difference between the cost obtained by the policy pi and the optimal cost over all offline policies for that same W. Okay, so the game we play is that a W is revealed to the offline controller, and it chooses a policy to, say, minimize the cost. We are presented with the same W, but in an online fashion, and have to come up with, and if we choose a policy pi, then this is the regret for that policy and for that particular realization of the process noise. Okay? So this definition of regret, you know, depends on the process noise. So it's a function of the disturbance. And so that's a little bit bothersome. And so we want to get rid of that. And there's two ways you can get rid of it. One is, again, to assume statistical knowledge of W and take expectation. So I can look at the expected regret. Okay, so if you look at the expected regret, because expectation is linear, it becomes the expected cost of your policy minus the expected, you know, best offline policy. And so once you look at this, you know, the second term, the expectation of the best offline policy, has nothing to do with pi. So it's just some constant term. And so what this suggests is that, you know, minimizing the expected regret is, you know, identical to minimizing the expected cost. Okay. So if I wanted to minimize the expected regret, I would just do an LQG controller. I would just do the standard H2 controller that minimizes the expected LQR cost. So this is not very exciting. And perhaps, not the right way to use the concept of regret. Okay, so instead what I'm going to do is I'm going to look at the worst case regret. So I'm going to look at the difference that we have here. And rather than take expectations over W, I'm going to look at the worst regret that can happen. Okay. Of course, as soon as I say worst case, I have to say in what sense do I mean worst case? And what that typically means is I have to say something about the set of sequences or disturbances from which I'm drawing my noise sequences. And so two common possibilities are bounded magnitude disturbances. So these are disturbances, whose magnitude at every time is bounded, or bounded energy sequences. And so these are all sequences that are bounded in energy, so-called L2 sequences. Okay. And in this talk, I'm going to consider bounded energy sequences. This is the same kind of approach that's used in H-infinity control. There also people focus on bounded energy. And I will remark that the results I describe here, kind of like H-infinity control, even though they're designed for bounded energy disturbances, they also apply to bounded power disturbances. But again, those are technical things I won't go into. So this will now be my notion of regret. Okay, so regret now is a function only of the policy pi, because I'm looking at the regret, the earlier regret, which is a function of both pi and W. But W here appears both in my online cost as well as in the best offline cost. The best offline cost also depends on W. And so I will look at this regret and I will supramize it, maximize it over all bounded energy disturbances. So that's what's written here. And so that is my notion of regret. Okay, so now I got rid of the dependence on W. Okay? So I'm looking at, what is the worst regret that I can get over all possibilities. So I'm deciding to make an action. I'm going to look at all possibilities of W in the future. And I am, making sure the regret is, I'm looking at the worst case regret. Okay. And so now if I define the set of online policies, so these are policies where U is only allowed to use current and past values of the disturbance. I'll call those pi superscript on. Then the problem we're proposing is the following. Okay, so now I have a regret which no longer depends on pi. This is the optimal regret. It's the infimum over all online policies of the supremum over all bounded energy disturbances of the difference between the cost of my online policy versus the best offline policy for the particular realization. So that's what we're going to look at, okay? So again, I'm sitting at time I, I'm looking at all possibilities that can happen in the future. I'm computing the regret, I'm looking at the worst case regret, and I'm minimizing the worst case regret. So that is formally what we want to do. So again, here I've rewritten it. This is what we want to do. So a few comments I think are in order. So this looks like a complicated problem. We have, two infs and a soup, and they're kind of in between one another. And they have, each of them have various constraints. Some are offline, some are online, some are over, bounded energy disturbances. So it looks complicated. And especially if you make it a little less abstract and actually plug in the LQR costs, it does look complicated. And so if you look at the literature in machine learning and statistics, when people study regret, regret problems are often complicated. Usually what is done and what people focus on is trying to figure out the scaling behavior of regret. So they usually look at regret over a finite horizon and try to see how it grows as a function of the horizon, whether it grows linearly or sublinearly or things of that sort. There are very few instances where the optimal regret or the regret optimizing policy can be explicitly found. And so one of the happy coincidences of this work that I'll describe, so in the context of LQR control, turns out you can explicitly find the regret optimal controller, and I will show you what it is in a bit. And we can explicitly also find the optimal value for the regret. Okay. So that's what I want to show you by the end of this talk. But before I do that, let me kind of give you a little bit of sense of what these types of controllers look like and how they compare to conventional ones. Well, okay, maybe that's the next slide. So maybe before I do that, let me just again, because I'm going to show you the performance of these various controllers, let me kind of contrast them in terms of what it is that they do. Okay, so I'm going to look at three different types of controllers. The first is the standard controller from stochastic control, the H2 optimal controller due to Kalman. It's sometimes called LQG control. And what it does, it looks at the LQR cost, does an expectation over the disturbances, typically assumes that the disturbances are white and Gaussian, and then minimizes that over all online policies. Okay, so that's the LQG controller. The H infinity optimal controller, although it's often not written in this setting, though this kind of, the way I've written it is equivalent to H infinity, looks at the cost, maximizes it over W's, and then minimizes it over policies. Okay? So it essentially does a min-max on the LQR cost. In the regret optimal setting, again, and I'm sorry if I'm repeating myself, the difference is we look at the difference between the cost and the best offline. Okay? So this is really the difference between the three controllers that I'm going to show. So in some sense, the Kalman filter has the best average performance. The H infinity has the best, worst case performance, and the regret optimal is whatever it is. Okay, so let me show you an example. So this is some, I believe, sixth order system, dynamical system that we looked at. So I should kind of explain to you what this is showing. So this is a frequency domain plot. And as we get through the talk, it'll become kind of clear why we're looking at frequency domain and what that means. So this is a discrete time system. So, frequencies are between 0 and 2 pi. And what I am looking at here is kind of the frequency response from, say, a sinusoid. If I excite the system with a sinusoid in the disturbance, I look at the LQR cost, if you will, for that particular input. Okay, so that's how I get a frequency response. And so the bigger the value, the higher the LQR cost, the worse that it is. So the red curve that you see here is the best offline controller. So it's a controller that has access to W beforehand and takes control actions. And so you can see at every frequency, it's better than the other three controllers. It dominates all the other controllers at every frequency. In fact, as I'll show in a moment, the offline controller dominates all the other controllers at every frequency for every possible disturbance. The blue curve is the LQG controller due to Kalman. It has the property, because it minimizes the average, that the area under the curve of the blue is the least for all possible causal controllers. So if you look at all possible causal controllers, there are none that will have an area under the curve less than the blue one. Okay? The black curve is the H infinity controller. Among all causal controllers, it has the smallest peak. Okay? And you kind of see it looks very flat. So it's a very conservative kind of controller. It basically almost behaves the same at all frequencies, but it's kept the peak as small as possible. The green is the regret optimal controller. And as you see, it kind of interpolates nicely between the H2 and the H infinity. So the H2 controller in this case is not very robust at low frequencies because the frequency gain to the LQR cost is high. It's around 9 point something. The H infinity has, its maximum frequency gain is 6 point something, I guess. So it's better, but the average performance is much worse. The area under the curve is quite large. And as you can see, the regret optimal controller interpolates very nicely between the two. I should have put in the numbers here. The area under the curve of the green is a smidgen away off the blue. So it's within 1 or 2% of the H2. And its peak is less than 10% off the peak of the the H infinity optimal one, whereas the H2 is about 50% worse than the H infinity. Okay, so this is the kind of behavior, and I'll show you, depending on time, more simulations as we go throughout. But the point being that the regret optimal controller interpolates very nicely between the other two. Okay, so for the remainder of the talk, I kind of want to get into how we actually solve this problem and some of the techniques that are used, because I think they are interesting. So recall we had this LTI system that I have over here. I'm going to define a signal S, which is the square root of the PSD matrix Q times X. The reason why I'm doing it is because if I define this S, then my LQR cost, especially if I take R to be identity, which was the weighting for the U term in the LQR cost, is just the energy of the S sequence plus the energy of the U sequence. And that will kind of simplify things for me. And I'm going to introduce a little bit of operator notation because the system here is linear and we will benefit from doing this. Okay, so if you look at the signal S, okay, it's a sequence. It's a double infinite sequence. It runs from negative infinite time to positive infinite time. It's a linear combination of the control signal, and the operator that maps that sequence to S I will call F. And likewise, G is the operator that maps W to S. Both F and G are causal operators because my state space system is causal. And what that means is when you write them as these doubly infinite matrices, they are lower triangular and they are toplets. In fact, in this case, they are strictly lower triangular because both F and G are strictly causal because UI influences xi plus 1 and therefore si plus 1, and so it's a strictly causal mapping. So there's zeros on the diagonal and above the diagonal. But you have this doubly infinite toplet structure, and what you put in every row of this matrix essentially is the impulse response, if you will, from U to S and W to S. Okay, so F and G are defined in this way. For F, you just put in BU. For G, you put in BW. So these are strictly causal operators. Okay. What about the controller? So it turns out, and I won't go into this, without loss of generality, you can assume the controller is also linear time invariant. So there's no need to look at nonlinear time varying controllers. One can prove that. I won't do that here. And so the controller, again, can also be represented by this lower triangular doubly infinite toplets matrix. Lower triangular, again, because the controller is causal. U is equal to K times W, where K is lower triangle. Okay, and so once you do that, S was FU plus G W, and so U is KW, so you can write everything in terms of W. So S is just FK plus G times W, and U, of course, was K times W. So everything is described by this operator with two blocks, the first block being FK plus G, the second block being K. Okay, so this really tells us how W maps to the S and U, which are the things whose energy gives me the LQR cost. Okay, so the LQR cost now is a function of the controller. I choose K, and of the disturbance W, and it's given by this quadratic expression here. I obtain that by just squaring if you're just computing the energy of S and U. Okay, so W again is an infinite sequence here, and TK is the two-block operator constructed from these doubly infinite operators Fk and G. Okay? It just is nice and concise notation. So it turns out that, and this is very simple, you can take a simple completion of squares. So what we cared about was this, Tk star Tk. So you can actually complete the squares on it, and it looks like this, where K naught is this expression here, which you can compute. And so when you look at this, it's kind of obvious that, so Tk naught is actually when you take K naught and plug it into this operator. That's what Tk naught is. It's kind of clear because this first term here, I plus F star F, is positive definite. So this term is always non-negative definite. It's 0 when you choose K to be K naught. But what it says is because this is always positive semi-definite, every controller is lower bounded by this non-causal controller K naught. So K naught is the optimal non-causal controller. and it dominates any other control. It gives you a lower cost on any control input, on any noise input, because this matrix is strictly, less than that. This difference is positive semi-definite. And so when I was showing you, earlier these simulations, that is really the reason why this red curve was below all the other curves at all frequencies. It's because in the context of full information control, there is a non-causal controller that dominates every other control. Okay. Okay, so let's now look at our problem in operator language, now that we've introduced that a little bit. So H infinity optimal control, recall, was this inf soup problem over the cost. The cost now, when we have a linear controller, as we saw, was just quadratic in W, and it was also quadratic in this TK. And we have to take a soup over this W and an inf over causal Ks. The regret optimal controller is exactly the same, except we subtract the TK naught star, TK naught term before we do the soup and the inf. Okay. And so that's what this implies. So now we can write this in terms of operator norms. The H infinity problem, okay, whenever you supramize over W of norm less than or equal to 1, that is nothing but the operator norm of TK star TK. That's the definition of the operator norm. Or it's the operator norm square of TK. So in H infinity, that's what you minimize. You minimize the operator norm of this operator, this transfer operator TK. In regret optimal control, you minimize the operator norm of this difference, because when we take the soup over W, the matrix sitting in the middle is this difference. So that is really the difference in operator language between H infinity and regret optimal control. Okay. It's also useful to understand this in the frequency domain. And again, for those of you who know these things, I apologize if I'm stating the obvious. But whenever you have a bounded linear time invariant operator with some Markov parameters or impulse response, so these are the entries that are on the diagonals of this LTI operator. This should be Fourier. I'm sorry for the typo. What you do is you take this impulse response, you compute its Fourier transform. If the operator is bounded, this converges. And it's well known that the operator norm of a Toeplitz operator, of an LTI operator, is just the maximum of the frequency response, which is basically the Fourier transform. So you can compute, if you will, or have formulas for these operator norms by going to the frequency domain. Okay? And so the consequence of that for H infinity and regret optimal control is in H infinity control, we are minimizing the peak of the frequency response, if you will, of TK. If TK itself is a matrix, not a scalar, then we pick up the maximum singular value. Same here for T, which is why I wrote, well, these should have been block operators. In regret optimal control, it's sigma max of the difference. That's the only thing that differs between these. Okay, so that's in the frequency domain what things look like. And so let's persist with this a little bit and see how we can actually solve this problem. Okay, so if you recall from the completion of squares, if you look at the square of the transfer operator for an arbitrary k, subtracting off from the optimal non-causal one, we had this term which was non-negative. That's the difference. So this is an identity. And so what I'm going to do is a trick that's, goes back to Wiener, I believe. So this quantity that we have here in the middle, it's a positive definite operator because it's identity plus something that's positive semi-definite. It's the conjugate transpose of something times itself. And so you can do a factorization which is akin to Koleski, or, I guess the reverse of Koleski. So I'm going to factor it in a way where the second factor here, delta, is causal, meaning that it's lower, and has the property that if you invert delta, it's also causal and bounded. So this is kind of like a Koleski. So the first term here will be upper. This one is lower, and the lower one should also have a lower inverse. Okay? If these are finite matrices, if something is lower and invertible, the inverse will be lower. If you have operators, it's a bit more tricky. But you can always do this type of factorization. And in the context of the state space models, we've looked at these factorizations are achieved through Riccati equations, which we'll see. Okay, so I can replace this I plus F star F with delta star delta. So this will be delta star delta. And so I can push the delta into this term. So I get delta K minus delta K naught. And delta star gets pushed into the term on the left. And because it has a conjugate transpose here, it comes in through from the right. Okay, so this is basically just the square of this quantity. And so that's very nice, because what we want to do, recall, looking back, the whole thing we're trying to do is to minimize the operator norm of this difference, okay? And so we recognize the operator norm of this difference to be the operator norm of this, but that's just the operator norm squared of, say, the term on the right, delta K minus delta K. Okay, so let's think of what this is saying. So K is a causal operator. Delta is a causal operator because that's the way I did the factorization. So it's the product of two causal operators. So it will also be causal, because both of them, they look at the current and past. Delta K naught is non-causal because K naught is non-causal. Okay, so think of here having a lower triangular matrix or operator, and here having one that has both upper and lower triangular parts. And what we're trying to do is to design this lower triangular part, because we have access to K, to minimize the operator norm of this. Okay, so we are essentially approximating a non-causal operator with a causal one in this operator. Okay, and that's what's known as the Nahari problem. And it's perhaps not surprising that in regret, this is what came about, right? So we are essentially approximating a non-causal operator with a causal one. And the reason why we're doing this is because we're really, comparing, the performance of our causal controller with a non-causal one. So it's not surprising that this problem came about. Okay, so Nahari looked at this problem in 1957, and just again formalizing the problem that he looked at. So he had a doubly infinite block Toeplitz operator M. So this just means it's an operator M, it's doubly infinite, and it's constant on the diagonals. And we want to find a lower triangular matrix, which again is doubly infinite block Toeplitz. So it's again constant on the diagonals, but it's lower. And I want to do it in such a way that the operator norm of L minus M is as small as possible. That's what Nahari looked at. There's a frequency equivalent of this as well, because of the fact that operator norms for these Toeplitz matrices are peaks of the frequency response or the Fourier transform. So equivalently, you can say if I give you a two-sided sequence, I want to find a causal sequence, so a sequence that is only non-zero for positive values of I, such that when I look at these things in the frequency domain, that the difference of the frequency responses is as small as possible in worst case. Okay, so I'm trying to approximate a non-causal function by a causal one, or sequence by a causal one, but the measure by which I care about how good my approximation is how well they match in the frequency. Okay, so, you might say, why on earth did Nahari look at this problem in 1957? It turns out this problem of approximating, causal sequences by non-causal ones and looking at the frequency response actually has a history in engineering, in particular in electrical engineering, and it does in filter design, okay? So, once people started, building electronic circuits and doing wireless and things like that, they really like to build filters like this, ideal low-pass filters. So if they had a signal that had a certain, bandwidth, they wanted to let the signal in, but very little noise. So people love to build these type of ideal low-pass filters, okay? So it's well known that these filters are not realizable. And the reason why they're not physically realizable is because the impulse response of this frequency, so the inverse Fourier transform of this frequency response, which is the impulse response of the system, is a sinc function, which is non-causal. So it can't be realized. So a sinc function means that if I apply an impulse at time 0, the sinc has values for negative time. So it has to anticipate that you're going to apply an impulse and start doing its sinc thing. So this is not a realizable filter. And so in the early 20th century, people were really struggling about how can we come up with causal approximations to this. And there's a whole bunch of work that's been done. If anyone has looked at filter design, there's a thing called Butterworth filters. These were designed by Butterworth in 1930. He was a British applied mathematician. There's a guy named Wilhelm Kaur who designed what are called Chebyshev and elliptic filters, and here you see examples of these type of filters. And so they were all interested in trying to approximate this kind of thing. They were engineers. They had other constraints as well because they wanted to build these filters with LC circuits, and so they were interested in rational approximations to this and so on. But I would encourage you, if you're interested, to look at this. In particular, Wilhelm Kaur has an interesting history behind him, and I think I'm short on time. Otherwise, I would have told you that history. So this is a problem that people have looked at, and so in terms of Nehari, I don't know what the motivation, whether he was motivated by filter design for looking at this problem or not, but he kind of looked at it fundamentally and said, okay, if I want to approximate some function, not just the step function or this ideal low-pass filter in the frequency domain, how do I do it, okay? And so to kind of give you a sense of what his solution looks like, so here is my non-causal operator. And I'm going to partition it. So I'm going to sit at the present, and I'm going to partition it into the past and the current, or the past and the present, and the future, okay? So M minus is the operator that maps past to past, M plus maps future to future, MH maps future to past, and MA maps past to future, okay? Oh, so this should be an L, I apologize, this second one. The operator L, when you partition, has nothing here because it's a causal operator. There is no mapping from the future to the past. And I should also mention that both L minus and L plus are also lower because this whole matrix L, again, that's a typo, is lower. And the other thing I want to mention is this operator that maps, future to past, which is kind of like the it represents the anti-causality of this M, is called the Hankel operator, because it kind of has the structure of a Hankel matrix. And so this is what it is. It's a semi-infinite matrix, and this is the structure. So it has the values of the impulse response M, if you will, for negative values. And if you fill it like this is the Hankel operator. And what Nehari showed, so he was interested in approximating this full M with the lower triangular L. And so he showed that if you try to minimize over this lower triangular L, this minimum value turns out to be the operator norm of the Hankel part, okay? And this is a very non-trivial result because you see if L minus and L plus did not have to be lower, then you could certainly eliminate M minus, M plus. You could also eliminate MA because LA has no restriction on being lower or anything like that. And you'd be left with MH, and that's the best you could do. You could never do better than the operator norm of MH. What Nehari showed was that even when you have lower triangular constraints on L minus and L plus, so that you cannot fully eliminate M minus and M plus, you can still arrange things in such a way that the operator norm that you get is the operator norm of the Hankel. Okay. And again, for those of you who are interested, there's a simple proof that one can give of Nehari's theorem by recursively using something called Parrott's lemma, which is actually a newer result. Because Parrott's lemma, first of all, is easy to show, and then once you show it, you can kind of recursively use it to prove this result. But in Parrott's lemma, you have a 2x2 block matrix. You have control over one block, and you want to choose it to minimize, again, the operator norm. And it turns out you can never do better than the operator norm of AB and BC, because they're submatrices of this matrix, no matter what you put here for X. And so Parrott's lemma shows that you can actually achieve that upper bound. Okay. How am I doing on time? I should wrap up quickly. So I basically gave you the ingredients of what's going on. Once you realize that you can reduce the problem to a Nehari problem, then you have to solve the Nehari problem. And so this is something that we did. And in doing this, I think we have a very succinct solution to the Nehari problem. I don't have time to go into it, but basically, whenever you have state space structure, and say some non-causal sequence that has, or anti-causal sequence that has state space structure, you can explicitly find the optimal, if you will, operator norm by solving a pair of Lyapunov equations, and you can explicitly also construct L. I won't go through this. I don't think there's any point, but it can be done. Okay, and so once you do this, once you have the solution to the Nehari, it's some work because we've reduced our problem to the Nehari. It involved the canonical factorization. It involves other steps. I won't go into them. But you can get the regret optimal controller. So first of all, you can get the optimal regret. Again, it's the maximum singular value of the product of two matrices that are found by solving these linear Lyapunov equations. Everything, there's B and U here. I have to say what A sub K is. A sub K is the closed loop matrix of the H2 controller, for those of you who know what that is. The K here is the LQR state feedback law. P here is the solution to the standard LQR Riccati. So it has a lot of elements of the standard H2 solution. So you compute these things, that's the optimal regret. And then the more interesting thing is the structure of the controller. So the controller has two components. It has a U hat component, which I will talk about momentarily, but it also has this component too. And for those of you who know what H2 control is, these two terms are the H2 controller. This is the LQR state feedback gain, and this is the part that is causally dependent on W. So basically, the regret optimal controller is a modification of the H2 additively, where this U hat is found from some nth order dynamical system. So there's some state which has the same order as the underlying dynamical plant. So your controller is nth order. And there's formulas for K and F, which depend on all the matrices. And there's another Lyapunov equation that you have to solve. So it's a very simple controller to implement. Basically, you need to solve one Riccati equation and two Lyapunov equations. Okay, so I'm kind of wrapping up, I think, time-wise. So let me show you a few more simulations, and then I will conclude. Okay, so this is an actual Boeing 747. I think we got it from Stephen Boyd's notes. So this is an actual, I guess, system that people care about controlling. And so what I'm showing you here is the operator norm from the disturbance to the LQR cost. The red, again, is the non-causal one. It dominates all the other controllers. Blue is H2. As you can see, it's non-robust at low frequencies. Black is H infinity. It has the same peak as the red. And green is the regret optimal. And as you can see, the regret optimal has, its worst case performance is a lot better than the blue is. This is the Frobenius norm of that same operator. And the reason why here I'm showing both is because the area under the blue curve in Frobenius norm is the expected cost. And again, if you look at the green, it's better over here, it's a little worse over here. And so when you look at the area under the curve, it's only a smidgen worse than H2, but considerably better than the H infinity. So as I said, it interpolates well between these extremes. I can also show you some time domain results. So this is, again, another linear system. We're exciting about white noise. The red is the LQR cost as a function of time. So this is not frequency domain, this is time domain. So we're exciting it with white noise. The blue is the H2 cost. It's optimal for white noise, and so you see it has the best cost. Green is the regret optimal, black is the H infinity, and so we're somewhere in between. The next curve is the worst case noise for that same system. So you can actually construct the worst case noise. Now the H2 is the worst, H infinity is the best, and we're again in between. So it interpolates nicely between these two things. So in conclusion, so there's certain extensions that we can do. I talked about the causal case. One can do strictly causal controllers. Again, for those of you who know what that means, these are probably more realistic from an implementation point of view. One can look at filtering problems. So in control, both H2 and H infinity, filtering and control are duals. Here they're not quite. So the filtering solution is more complicated, quite a bit more so. One can look at measurement feedback problems, so where you don't have access to the state or you don't have access to the disturbance, but rather what you have access to is a measurement of the state or a noisy measurement of the state or a partial state. Again, the solution is more complicated, but can be done. One can look at finite horizon problems. So here I looked at infinite horizon. So you can compare yourself to a non-causal controller that doesn't see the infinite future, but say 10 steps ahead or 20 steps ahead, whatever you want. And this is I think will be of use if one wants to regret optimal control in the receding horizon setting. We can extend these things to time-varying systems. And finally, there's, this kind of idea of regret is kind of like a philosophy. So, you can have other measures for regret, not necessarily just what I did. So what we looked at here were bounded energy or bounded power disturbances. It might be possible to look at, bounded amplitude disturbances. In robust control, that's called L1 control. Might be possible to do it with regret, I don't know. But, when you do regret, you compare to some controller and you look at the difference between, you regret how much you didn't use that controller. So I think this idea can also be used in decentralized control. So you can compare yourself to a centralized controller and say, I want to design a controller so I have the least regret for choosing this control structure as opposed to one that was centralized. And it would be interesting to see what kind of control designs come out from that. So I know I rushed it a little bit at the end, but in conclusion, what I want to say is I believe this idea of regret optimality is a viable option for control system synthesis. The controllers are quite simple. They share many of the characteristics of H2 and H infinity controllers that people use frequently in industry and in applications. And I think these controllers interpolate very nicely between them. They often have performance that's a smidgen away from the best performance of the H2 and the best performance of the H infinity simultaneously. So I think I'll stop here, and if there's time for questions, I'd be happy to.
Yeah, thank you so much for this great talk, Babak. We do have some questions. Let me select some questions. We have so many questions. So we have two questions regarding the frequency plot. So the first one is, can we say something about the regret optimal curve? For example, the area under this curve is smallest, or like the distance between this curve to the red curve is the smallest.
Yeah, so that's precisely correct. The correct interpretation is that it has the smallest worst case. So for example, if I look at the first one that I showed you, this one here. So the green curve has the property that its distance from the red curve, the worst case distance from the red curve is the least. So for example, the black one has a big distance here. The blue one has a big distance here. I don't know which point on the green has the worst case, but this has the least worst case distance from the red. That is the frequency domain interpretation.
Cool. And another question is, why does these three curves meet at some common points? I mean, the H2, H infinity, and regret optimal curves.
That is a good question. It meets here. I don't know. I think that's an artifact of this particular system. I'm not sure if that's true for the other one, but that is an interesting. I do not know the answer. It's not true, generally speaking. If you look at
right. Another interesting question regarding the optimal regret, the regret optimal policy. Can we have some dual result for the worst case W? So we have some result tell us the optimal U. So what is the optimal W when we solve this?
Yeah, so the worst case W, you can see, so for these LTI systems, it's not true for finite horizon or time varying systems, but for LTI systems, the worst case disturbances are sinusoids at whatever frequency these, these guys peak. So for this particular example, the worst case disturbance is actually DC. It's a constant signal. But you can identify the worst case for LTI systems by looking at where the frequency domain peaks. For finite horizon or for time varying systems, you just have to compute TK and look at the maximum singular vector. The maximum singular vector will tell you what the worst case W is. It will give you the direction of the worst case W.
Thanks. Another question from Bayu, like for filtering problem, how to relate regrade filtering to the mixed H2 and H infinity filter?
So I'm not sure I follow exactly what that question is. I mean, so the filtering problem, as I said, is a little bit, it's not exactly the dual of the problem I described, which was the full information control problem. But in filtering problems, you can also write as a mapping from, say, the disturbances in the system or the measurement noise or whatever you have to the estimation error. So again, you can define an operator there. It's a function of your filter, and you can compare again, the best, a causal filter with a non-causal one, which is typically called the smoother. In terms of the structure of the solution, so here, the solution was the H2 solution plus a modification. There was an nth order control system that modified it. For the filtering problem, it's more complicated. I'm not sure if I can tell you exactly what that is. I mean, if there were time, I could explain it. It's not quite the dual. The reason why it's not quite the dual is because in one case, you have like TK star times TK minus that thing. And the other way, they change. And so it becomes something like a 4-block problem if people know what that means. So the filtering problem is a lot more complicated.
Thanks. Let's answer the last two questions. The first one is from Nakmia. Is there some separation principles here? I imagine something like common separation principles.
Yeah. So the measurement feedback problem we're looking at right now, and we have a solution, but we haven't simplified it as much. I would hope so, but I haven't been able to pull it out yet. So because even if you look at the H infinity measurement feedback problem, there is a separation of sorts, but it's not as nice as the separation that you have in H2, where you can just say, I can take the optimal, full information controller and just run a Kalman filter to estimate, the state there. Even in H infinity, it's a little bit more complicated because the Riccatis you get are somewhat coupled. Here, that is certainly the case. So you won't have a separation principle as nice as in H2. Whether you will have one even as nice as in H infinity, I don't know.
Thanks. Last question. So you see here, we will extend to strictly causal case. Does it mean so even WT is not given to the controller? So right now I see the WT is input to the controller.
So the strictly causal case means that WT is not given. And so what happens in the strictly causal case is that this term vanishes. So you have a state feedback term, which is identical to the state feedback in H2. And this U hat is a little bit different because U hat here, if you look at this formula, there's a WT here. So U hat is a causal function of W. And so in the strictly causal case, these matrices change a little bit, and I don't remember exactly how. But most importantly, this term, the direct term from W to U hat goes away. But the structure is the same. The structure turns out to be the strictly causal H2 solution plus a modification where the modification is an nth order control.
Cool. Thanks so much for the great talk, Babak. Sorry for those questions I didn't cover due to the time limit. Yeah.
Okay, well, thank you very much. I hope I didn't rush too much, but yeah, if anyone is interested in more in this stuff, feel free to email me or I'd be happy to share more.
Yeah. Thanks so much, Babak, for giving such an interesting talk. I guess we will post the videos later on YouTube, so stay tuned. And just a reminder, there will be no seminar next week. So I'll see you all like on October 21st. Thanks.